The United States electrical system has features that some find outdated. One perspective is that the grounded system, a common configuration in the US, is antiquated compared to alternative approaches used elsewhere. This viewpoint stems from an electrical power engineer. Grounded systems were initially implemented for safety reasons, providing a path for fault currents to return to the source, thereby tripping circuit breakers or blowing fuses and energizing the circuit. This reduces the risk of electrical shock. However, grounded systems also have potential drawbacks. Firstly, a ground fault can create a circulating current, leading to energy losses. Secondly, grounded systems can be more susceptible to voltage sags and swells, which can damage sensitive equipment. Thirdly, the reliance on a single point of grounding can make the system vulnerable to ground faults, potentially disrupting the entire system. Alternative systems, such as ungrounded or impedance-grounded systems, offer different characteristics. Ungrounded systems do not have a direct connection to ground, which can reduce the risk of circulating currents and improve system reliability. However, ungrounded systems can be more difficult to troubleshoot because ground faults do not immediately trip circuit breakers. Impedance-grounded systems use a resistor or reactor to limit the current flow to ground during a fault, providing a balance between the benefits of grounded and ungrounded systems. The Swedish electrical system, specifically, often employs different grounding techniques and protection schemes. It's designed with a strong emphasis on reliability and minimizing disruptions. While the specifics of the Swedish system would require in-depth analysis, its general approach often involves more sophisticated monitoring and control systems. The preference for a different system also involves the consideration of the overall grid architecture. Modern grids are evolving towards smarter, more resilient designs that incorporate distributed generation, renewable energy sources, and advanced control systems. These systems often require different grounding strategies to ensure stability and safety. The debate over the best electrical system also involves economic considerations. Upgrading an existing system can be costly and disruptive, so any proposed changes must be carefully evaluated in terms of their benefits and costs. There's no one-size-fits-all solution when it comes to electrical systems. The best approach depends on a variety of factors, including the type of load being served, the characteristics of the local environment, and the available budget. The suitability of an electrical system also depends on its application. Industrial facilities, for example, may have different requirements than residential areas. Industrial facilities often use three-phase power systems, which provide higher power capacity and improved efficiency. Residential areas typically use single-phase power systems, which are simpler and less expensive to install. The choice of grounding method also depends on the type of equipment being used. Sensitive electronic equipment, such as computers and medical devices, may require special grounding to protect against voltage surges and electromagnetic interference. The effectiveness of an electrical system also depends on the quality of its components and the workmanship of its installation. Poorly installed wiring or faulty equipment can compromise the safety and reliability of the entire system. Regular maintenance and inspection are essential to ensure that the electrical system is functioning properly and that any potential problems are identified and corrected before they cause a major failure. The discussion of electrical systems also involves regulatory considerations. Electrical codes and standards, such as the National Electrical Code, or NEC, set minimum requirements for the design, installation, and maintenance of electrical systems. These codes are designed to protect people and property from electrical hazards. Electrical codes are constantly evolving to keep pace with technological advances and to address new safety concerns. Firstly, the NEC Article 250 covers grounding and bonding requirements for electrical systems. Secondly, the NEC Article 300 covers wiring methods and materials. Thirdly, the NEC Article 400 covers flexible cords and cables. Fourthly, the NEC Article 500 covers hazardous locations. Fifthly, the NEC Article 600 covers electric signs and outline lighting. Sixthly, the NEC Article 700 covers emergency systems. Seventhly, the NEC Article 701 covers legally required standby systems. Eighthly, the NEC Article 702 covers optional standby systems. Ninthly, the NEC Article 705 covers interconnected electric power production sources. Tenthly, the NEC Article 725 covers Class 1, Class 2, and Class 3 remote control, signaling, and power-limited circuits. The implementation of electrical systems involves a wide range of professionals, including electrical engineers, electricians, and inspectors. Electrical engineers design electrical systems and specify the equipment and materials that will be used. Electricians install and maintain electrical systems following the plans and specifications provided by the engineers. Inspectors ensure that electrical systems are installed in accordance with the electrical code and that they are safe to operate. The ongoing development of electrical systems is driven by a number of factors, including the need for increased efficiency, improved reliability, and enhanced safety. Research and development efforts are focused on developing new technologies such as smart grids, advanced metering infrastructure, and renewable energy sources. Smart grids use advanced communication and control technologies to improve the efficiency and reliability of the electrical grid. Advanced metering infrastructure allows utilities to remotely monitor and control electricity consumption, enabling them to better manage demand and reduce energy waste. Renewable energy sources, such as solar and wind power, are becoming increasingly important as the world seeks to reduce its reliance on fossil fuels. The integration of renewable energy sources into the electrical grid presents a number of challenges, including the need for improved grid stability and the development of new energy storage technologies. One technology is batteries, another is pumped hydro storage, and a third is compressed air energy storage. These systems store energy when it is plentiful and release it when it is needed. The discussion of electrical systems can also involve a consideration of power quality. Power quality refers to the characteristics of the voltage and current in an electrical system. Poor power quality can cause equipment to malfunction or fail. Common power quality problems include voltage sags, voltage swells, harmonics, and transients. Voltage sags are brief reductions in voltage that can cause equipment to trip or shut down. Voltage swells are brief increases in voltage that can damage sensitive equipment. Harmonics are distortions of the voltage and current waveforms that can cause equipment to overheat. Transients are sudden, short-duration voltage spikes that can damage electronic equipment. Power quality problems can be caused by a variety of factors, including lightning strikes, switching operations, and the operation of certain types of equipment. Power quality problems can be mitigated through the use of power conditioning equipment, such as surge suppressors, voltage regulators, and harmonic filters. The design and operation of electrical systems also involve a consideration of electromagnetic compatibility, or EMC. EMC refers to the ability of equipment to operate without causing interference to other equipment. Electromagnetic interference, or ME, can be caused by a variety of sources, including radio transmitters, computers, and industrial equipment. EMI can disrupt the operation of sensitive electronic equipment. EMC problems can be mitigated through the use of shielding, filtering, and grounding techniques. Electrical systems are a critical part of modern infrastructure, providing power to homes, businesses, and industries. The design, installation, and maintenance of electrical systems require specialized knowledge and skills. Ongoing research and development efforts are focused on improving the efficiency, reliability, and safety of electrical systems. The debate over grounded versus ungrounded systems continues, with engineers and electricians offering different perspectives based on their experiences and the specific requirements of the application. The choice often depends on factors such as safety requirements, cost considerations, and the sensitivity of the equipment being powered. The comment about spoken English highlights the challenges of cross-cultural communication. Even when individuals share a common language, differences in pronunciation, accent, and slang can make it difficult to understand each other. Effective communication requires patience, active listening, and a willingness to clarify any points of confusion. The electrical engineer's perspective provides a valuable insight into the complexities of electrical systems and the ongoing efforts to improve their performance.